All right, let's work on the second problem of the day, which is LeetCode number 79, word search. Given an m by n grid of characters board and a string word, return true if word exists in the grid. The word can be constructed from letters of sequentially adjacent cells, where adjacent cells are either horizontally or vertically neighboring. The same letter style may not be used more than once. Okay. Let's see. So this seems like a graph problem to a certain extent. And you could reword it to be, consider each letter as a node and each adjacent set of nodes to have an edge unweighted and no direction, undirected is the term, between them. And then the question in this case is, can you reach, or can you create a path, or I guess, does a specific path exist within the board? Or I guess the graph in this case, right? If we're pulling it straight, completely into the graph analogy. Right, so each letter counts as a node, and if they are adjacent, then there is an edge between them, unweighted, undirected. And the question is essentially asking whether or not a path exists within the graph. Well, in this case, we could use probably, I think DFS would work. BFS too, but it might be slower. Not sure on that. The idea is, the reason why I say DFS may be faster than BFS in this case is because if we have a suitable candidate, then it makes sense to pursue the path that is the most viable for now, rather than checking candidates that we've seen before, or rather than checking all the potentially viable candidates, right? So if this A was surrounded by B here, it doesn't make sense that, or in that case, we would be running essentially a BFS because there's really no rhyme or reason as to the direction. But in this case, we would probably want to, once we see this C right here, right, we would probably want to pursue this path down rather than checking the adjacent cells for the other ones. The main problem, I guess in this case, is that we cannot reuse a cell more than once per try, I guess, would be the best way to think about this. So per attempt of creating a word, we cannot use a cell more than once. So for example, we can do A, B, C, C. Let's say D existed here, right? And this, or this was E, and this was D, right? And this didn't exist. We could go with the path like this, or we could go with the path like this. Yes, C and all these other nodes are used more than once, but they are only used once per attempt of creating the word. So that leaves maybe some sort of data structure / storage in order to mark cells as sort of visited in our attempt, or at least keep a running check of them. So let me think about this. If we use a DFS, Well, a set in Kotlin remembers the order in which elements are added. And the reason why I'm leaning towards a set is because a set provides us with a O of 1, a constant time lookup. And we need that additional lookup in order to remember the cell in which we have visited. We could also attempt to use a matrix, basically create a copy of the matrix that is 0 and 1, or true and false, basically a boolean matrix to mark the elements that we visited. That could also work. Let me think. Let's try to turn this into a procedure. So first, iterate over all elements within the matrix. So this is O of m times n. And what we want is to keep a list of all possible entry points, which is word at 0. Is word potentially... The word length is at least 1. Okay. So we can safely do word at index 0. Then run a subroutine over all possible entry points. This subroutine is going to be check in the 4 cardinal directions whether the next item exists. If true, or if found, add to a set of coordinates that we have searched and recurse on that element. Finally, remove that element from our set of searched coordinates and return. And the reason why we want to remove that element from our set of searched coordinates at the end, as far as I think, is that if we want another procedure to use the same set of coordinates, or if potentially there is an offshoot here, that may potentially reuse elements, then we want to make sure that we don't limit those options. I think. I could be wrong on this. This potentially, assuming that the board is just one giant word that just snakes around, or something like that, it could potentially iterate over all elements within the matrix. So, and I mean, given the algorithm itself originally, like the base algorithm, I do not think that there is a way to improve this algorithm over or beyond O of m times n. we could potentially achieve a better runtime through other means. I know that there was a follow-up here talking about search pruning, but that's something that I have no idea about. So, not my area of expertise, but definitely something that I will look into. So, let's give this algorithm a shot, and then let's see where it takes us. So, we can say val. We are going to need a data class, coordinates, row, which is an int, column, which is an int, or we can say board dot for each row for each cell, column index cell. This will be indexed, column, or sorry, row index. Well, if word.length is 1 and cell equals word at 0, we can just return true. If it exists and the word length is 1, we found it. Otherwise, we can just add into our val entry points, which will be a mutable list of coordinates. And we can say entry points add coordinate, which is row index, column index. Right, so that's our initial array, or initial routine, to add all the potential entry points within our entry points. And then we can say search is, I guess, the next one. We'll definitely need our board char array. We'll definitely need our word. And I do wonder. Current cell coordinate. Then we can say entry points for each point. We will run a search. We can say if the search board returns true, then we return true. Point. And we need our board, we'll need our word, need our point. And then otherwise, return false at the end. So this search function will essentially act as a DFS. And DFS, unlike BFS, is recursive. Shout out to Cracking the Coding interview for reiterating on that. And essentially what we will do is that we need to keep a current actually index. We kind of need to keep a current index on sort of where we're at. In terms of the word. And then we can say if board dot, or yeah, board at, or we can say current cell dot row -1 if we go up a row is greater than board dot size, else if current cell dot row plus 1 is less than, actually this should be greater than 0. And this should be less than board dot size. And these should just be independent cases. If current cell dot column -1 is greater than or equal to board at row dot size. Actually, no, this is greater than or equal to 0. And if current cell dot column plus 1 is less than that. And then at the end, we just return false, and this will return a boolean. Well, we can say that if board at the current cell dot row -1 and the current cell dot call is equal to the word at the index plus 1. So if it matches the next letter that we're looking for, let's see, far up, far down, left, right. Then our up will be equal to our search result from our board, our word, our index plus 1, current cell. Well, if index plus 1 is equal to word dot length -1, return true. If yeah, because if this is true, that means that it matches our next letter. And if our next letter is the last letter, then we can return true. And this will be very, very similar to each of these. So if this plus 1, then this will be down because we're going row that way. And this will be a coordinate of current cell dot row -1 and current cell dot column coordinate current cell dot row plus 1 current cell dot column and this is column -1. This will be a coordinate of current cell dot row and current cell dot column -1. And this will be left, and this will be right. Current cell dot column plus 1. Return up or down or left or right. So if any of those end up returning true, then we're good. Let's see. Board, word, and index plus 1. Yes, those remain the same. Row minus 1. Yep. Row plus 1. Yep. Column minus 1. And column plus 1. These two minus 1s are greater than or equal to 0. Yep. This index part will not change. Yep. Row minus 1. This should be column plus 1. Everything else seems fine. So the idea is that it'll check the 4 cardinal directions, starting with up, then down, then left, then right. Of course, making sure that those are valid moves first. And then it will check to see and then it will recurse on those elements if they happen to be valid for the character that we're at. So let's go ahead and run this code, and let's see if there are first any compiler errors, and then if there are any, this should be val, both of these should be val. We totally forgot, or I totally forgot about the whole cannot visit something twice. We'll get to that in a bit. I just want to clear up all the errors with this first. Should be current cell. Board line 20. Oh. Current cell dot row dot size. So that should solve that. And val entry points. This should be a mutable list of. But yeah, we do need to consider duplicates now. So we've gotten sort of like the basic part running, and it seems to be accepted. And now we need to think about, okay, let's mark the sets or the characters that we've used and we cannot use again. So this will also take in a set. We'll say ignore list, which will be a set of coordinates that we will ignore. And this will be initialized as empty set. So if something exists and ignore and not ignore list contains a coordinate we'll just say val up coordinate so that this is a little bit not as messy. Okay. I mean, it'll still be pretty messy, but up coordinate dot row up coordinate dot column. And then we can just pass this in. And if it does not contain it, then we will add it into our list of items to ignore. Coordinate is equal to current cell dot row plus 1 current cell dot column. Then we can do this and not ignore list contains this. Then we would do ignore list dot add this. And we will send our ignore list down here. And then we can say val left coordinate is coordinate current cell dot row current cell dot column -1. We can just add this here. We'll pop in our ignore list and not ignore list dot contains left coordinate, not ignore list contains right coordinate, which has not been made yet. Cell dot row current cell dot column +1. This right coordinate can go here. Our ignore list can get popped into there. Okay, and then like I said, once we're done with it, we can do current or ignore list dot remove up coordinate. And the reason why we do this is that we don't want to inhibit any other sort of traversal, which is down the stream from here, from sort of, and technically we don't need to do it for that one, but we don't want to inhibit the other paths from potentially using a cell that we have used. What is the actual... This should be a mutable set then. And mutable set. Is there an empty mutable? We could just do mutable set of nothing. And hopefully that works. Looks like we got a bad answer for the last one. Okay. Let's see why. We can do print line coordinate. The good thing about the awesome thing about Kotlin is that data classes print out like log out very, very nicely on their own without any additional formatting. And then we can say ignore list. I don't know if ignore list will print out that well though. So we are looking at A, so 0, 0, 0, 1, and then 0, 2. So 0, 0, when we move here, oh, we should add our current cell. Not our previous. And actually, let's move that one below so that our returns are even faster on a very, very marginal level. I think we actually want... So when we spot this, we want to add our current value to our ignore list. So don't use this value for now. We move here. Okay, we go to B. B is fine. We see C over here, so we move to this. We ignore B now. And then now we can check here. Okay, I think that works then. So we want to add our current cell to our ignore list, not our next cell. Awesome, awesome, awesome. Looks like that is working now properly. Let's run through all of our example test cases. We might actually end up tossing an issue there. Yeah, we'll leave the print line here in case we run into any iffy cases. Just throw in a submit, and let's see if we actually get a right answer. Okay. Why did this return true? This case is wrong. If cell is equal to word 0, then if word.length is 1, then we return true. Otherwise, we just add this. We only want to return the entry points, or we only want to get and add entry points. Well, if there actually is an entry point, right? So this should be correct now. Right. Okay. Let's see if there's any other issues that we need to deal with. Nope. Looks like it works. Just one off of 1,000 milliseconds runtime. Awesome. Honestly, I'm quite happy with this. I'm going to take a look at the solution off camera to take a look at what this whole search pruning thing is. I think that would be kind of interesting just to figure out what it does. But in any case, that's all for this problem. So we didn't do particularly spectacular for the runtime and memory usage, I'll admit. But it's all right, I feel. And in any case, I hope you learned something, and I'll see you for the next problem.